So I'll start the recording now. Okay, welcome everyone. Today's speaker is David Aspero, and he will be talking about, how do you actually pronounce this? I don't really know. Star axiom and surrounding issues?
Yeah, star, yeah.
Okay, star and surrounding issues.
Okay, thank you very much. Thank you very much also for inviting me. So I'm going to talk about things related to, I'm going to give the proof that Martin's maximum double plus implies star. I'm going to give the full proof of that, and I'm going to talk about some work surrounding this result. So I know that Ralph gave a talk about, that was around a year ago, about this topic. So my talk will be a bit different. He didn't actually give a full proof of the theorem, which I'm going to do here. And as I said, I'm also going to talk about this surrounding issues. Okay, so interrupt me if I'm missing to define things or whatever. And
we always do.
Yeah, right. So let me get started. So by defining star, which is well, in the 1990s, in the early 90s, Wooden defined and studied the following axiom. He called star, which says two things. So one thing is that the axiom of the determinacy holds in L of R, so it's something you get from large kernels. And the other thing is that the inner model L of P omega 1, right, is a P max extension of L of R. Okay, so we have this nice inner model of L of R, which is very well understood if there are large kernels around. So so will be its theory will be invariant under forcing and will satisfy AD. And then you're saying that this larger inner model, where fragment of the universe where things like CH lives, or Susan hypothesis or many other things, is a forcing extension of the first one by some forcing Pmax that I have to define next. Okay. Okay. So this is a definition of Pmax forcing. All right. So you have so first of all, I need to talk about what's a generic iteration of some countable transitive model of some set theory. Okay. So I have some eta at most omega 1, and then I have a sequence of M alpha, I alpha, and then I have some G alphas will be generic filters, and then some J alpha beta that will be some elementary embeddings between these models, right? So I'm saying that this is a generic iteration of the first model, M0, I0. Well, if and only if M0 is a countable transitive model in all of Z of C. So let's write sort of C star. Let's say that sort of C without power set axiom. Then I0 is a subset of M0, and the subset of its P omega 1, and it such that M0 and I0 thinks that I0 is a normal ideal on omega 1. So typically this will be the non-essential ideal, but could be other ideals. Okay. Then the J alpha betas, as I was saying, for alpha less than beta less or equal than this length, is a commuting system of elementary embeddings, okay, between the M alpha, the alpha model, and the beta model. Okay, so they commute. And then at successive stages, what I do is I say that G alpha I pick G alpha to be a generic filter for P omega 1 mod I alpha as computed in M alpha, right? That's a generic filter over M alpha, and then M alpha plus 1 is just the ultra power by this generic filter, and J alpha and I alpha plus 1 is just the image of I alpha to this under the ultra power. Okay, and J alpha plus 1 is just the ultra power embedding. Okay. Now, if beta is a limit ordinal, then M beta is going, and and the J alpha beta will be the direct limit of everything so far. Okay. So this is just right. So this system of as I'm saying, this commuting system I mentioned embeddings, where at the successive stage you go from alpha to alpha plus one by building this generic ultra power, by this generic filter over the current p omega 1 modulo the current idea. Okay, so then I say that so feel a pair Mi is iterable, even only if the models that you get in every generic iteration of Mi are well-founded. So not just the first model. Think of this as a model of Z of C. Okay, so it's not just saying that that M thinks that I is precipitous, right? So that would mean that the first generic ultra power of the universe is well-founded, but also that externally in reality every generic iteration in this sense will be well-founded. So that in principle is a stronger statement. So now here's the definition of Pmax forcing. So a condition in Pmax is a triple MIA, where Mi is an iterable pair, right? So it's this countable, so it's countable transitive model, which is it's iterable in this sense. So being iterable, if you think about it, is a pi 1-2 statement about Mi so far. And then M is a model actually of Martin-Zagsin omega 1, and that's convenient. A is a subset of omega 1 in M, okay, and M sees things that A is rich enough, so A computes omega 1 correctly, okay. Okay, so it's not it's some complex set. It's not some set in L of R, say. And then the extension relation is given like this. So a condition M1 is stronger than M0, even only if M0, the weaker condition is a member of M0, right? And moreover, in M1, in the universe of the strong condition, and in M1, there's a generic iteration of the weak condition. Okay, so this is generic iteration of M0, I0 of length, it's omega 1, right? Which sends the distinguished set of the weak condition to the distinguished set of the strong condition, right? So it stretches it out to the new distinguished set. And moreover, this iteration, this generic iteration, is correct in the strong model, in the sense that everything in the ideal of the weak condition is sent to the ideal of the strong condition, and moreover, every positive set in the final model is really I1 positive. It's really positive from the point of view of the strong condition. Okay. So the ideal, so being in the ideal and being a positive set in the ideal line up nicely, coherently. Okay, and this distinguished sets are are getting larger and larger. They are yes. This condition.
But positive means not a subset of a set in the ideal, or
positive means not in the ideal. Yes.
Oh, I see.
Yeah. So think of this as stationary. Yeah. I mean, actually, the non-stationary ideal will be the typical ideal. You could actually do everything just with the non-stationary ideal. Okay, so you could define this forcing also, changing the definition a bit, where you take models of some theory or another, and you could take, the ideal to always be the non-stationary ideal, and then you get the dense suborder of this, so you get essentially the same forcing. Okay. All right. So some properties of Pmax under AD and L of R. Well, first of all, I mean, this forcing lives in L of R, right? It's something, it's defined. So all these countable transit models live in L of R, right? They call it by reals, and then being iterable is a pi 1-2 statement. So it's absolute between L of R and V, right? and all the other conditions are, some are things that L of R can correctly recognize. Okay, so L of R defines Pmax correctly. So some properties of this forcing on the AD. So for one thing, it's homogeneous, which means that if you have any conditions in the forcing, you can go to two strong conditions so that the cones below these conditions are isomorphic. So in particular, Pmax will, for every condition, will force the same truth value about any statement with parameters in the ground model in L of R, right? So also Pmax is sigma closed. So in particular, if you have DC in L of R, then it's not going to add new reals. All right. So if you start with a V, satisfying DC, this will be inherited. So you're not adding reals if you force with Pmax. Okay. Now, if G is a Pmax generic filter over L of R, then the extension, start with a model of, where choice fails quite badly, model of AT, but suddenly, so you are forcing choice. So you have a model of ZFC. And if you define AG as the union of all distinguished sets that come from the generic, okay, then this G, the generic filter, can be computed in L of R together with this one subset of omega 1, and it can be computed in this way. It can be computed as the set gamma AG which is formed by those Pmax conditions MIB, such that there is a correct iteration. There's a correct iteration of MI relative to my real non-Fisher ideal. Okay, so in extension, which sends a distinguished set B to AG. Okay, so that's how you can define the generic filter. And in fact, given any subset A of omega 1 in the extension that computes omega 1 correctly there, gamma A, so the same set will define relative to A, can be computed in L of R when we throw in A, and it will be a Pmax generic filter over L of R, and then L of R together with that filter is L of R G. So it's the same model. So in particular, it follows that this extension satisfies that V is L of P omega 1, right? Because you just added this new subset of omega 1, and actually any subset of omega 1 which is not in L of R, which computes omega 1 correctly. And so this extension will be a model of star if L of R was satisfied AD and G was Pmax generic for L of R, right? Because you didn't change, you didn't add any new reals, so still have this. So this model recognizes that this G is Pmax generic over L of R.
But the way you defined star, it could hold in a bigger model too, right?
Yeah, well, that's what we're going to prove. I'm going to prove that that does imply star, right?
Oh, I see.
What I'm saying here is that you can trivially get a model, or sort of trivially get a model of star just by forcing over L of R. Okay. Yeah. Now the point is that, of course, this model won't have real large cardinals, right?
What I mean is if star holds really only depends on whether there exists such a G, right? It doesn't depend on the rest of V.
Exactly.
Yeah. Okay. I see.
Right. So far, right. Notice that you have a model of star, but which doesn't have large cardinals, doesn't have even measurables. Sure.
And from this slide on, you are working under some kind of large cardinal assumptions in V, right? So to make everything work.
In this slide?
Yeah, I think from this slide on, probably.
Well, I'm still assuming AD for what I'm going to mention. Well, sure. In this next slide, I'm going to say. I'm going to assume that that I have a proper class of leading cardinals. Okay. So, right.
I think so far we've only used that AD holds in L of R, right? To get that exactly. Pmax has nice.
Yes, exactly. So far we've just looked at let's see, right? I mean, properties of this generic extension of L of R, right? So now let's see how that relates to V, right? Or yeah. So now suppose that let's see. So now you have the pi to maximality theorem, which says the following. So suppose you have enough large cardinals, say proper class of wooden cardinals, okay, in a model of Z of C, okay. And now you take a G, which is Pmax generic over L of R, right? Okay, so so far just you know, I mean, for example, typically if you know, you have a model of CH, you will have lots of these generic filters, okay, over L of R, or otherwise you just force. Now, okay, so you take this G Pmax generic over L of R, may or may not be in V, right? And Q is a set forcing in V, and you take H, which is a Q generic filter over V, and now you take any pi to sentence sigma such that this structure here, so H omega 2 with a non-saturated ideal of on omega 1 in this extension thinks V of H thinks that sigma holds. Well, okay, so you have this, right, this generic extension of V, and in there H omega 2 satisfies this pi to sentence sigma. Well, then if you go down to L of R and G, right, then that sigma is also satisfied in its H omega 2, right? So this the H omega 2 of this Pmax extension of L of R will satisfy all pi to statements that you could possibly force over to hold in H omega 2 over V. Okay, then you have this completeness modulo set forcing that says, well, suppose again you have enough large cardinals, say a proper class of wooden cardinals, then you take any two set forcings in Q and you know, any two set forcing extensions of V, and go to you know, go to their L of R's and take take generic filters for the corresponding Pmax forcings, then these two extensions have the same theory. Okay. So all models that you get of star, if you have these large cardinals, will satisfy the same theory of L of P omega 1. Right? Now, the proof of the completeness result is easy. So take sigma be any let sigma be any sentence and suppose that it holds in one of the models, right? But then by homogeneity of Pmax, you have that L of R dot model PH0 thinks that Pmax, you know, the empty condition in Pmax forces sigma. But now the theory of L of R is invariant under forcing if we have these large kernels, and Pmax is a definable forcing. So you know, in the L of R of the other model, you have the same thing. The Pmax forces sigma, and therefore that the extension satisfies sigma. Okay. So right. So far we've seen these three properties, right? That will make star a nice axiom. So we have this pi to maximality, which says that you have star and you have large cardinals. That implies that H omega 2 with this extra predicate with non-saturated ideal will satisfy all forcible pi to sentences over that structure. And then you have a minimality property, which says that tells you that star implies that L of P omega 1 is a form just adding the least possible thing to L of R, which is a subset of omega 1 that computes omega 1 correctly. So it's really a minimality condition, right? So which makes this L of P omega 1 sort of a canonical model, right? And then you have this completeness property, which says that you have star and you have large cardinals. Then that provides a complete theory for the model L of P omega 1 modulo set forcing. Right? So any two models of star obtained by forcing will agree on the theory of L of P omega 1. Okay. So the question was whether whether star is a really nice axiom, and that would mean that it's compatible with all consistent large cardinals in V. That that may exist, right? Okay, so is star compatible with all consistent large cardinals? Because as we already saw, so you just take the Pmax extension of L of R, then that will satisfy star. But sure, it doesn't have large cardinals. Actually, it certainly doesn't have wooden cardinals, which would make star interesting, right? So is star compatible with all consistent large cardinals? And in fact, well, does in fact star follow from MM double plus, right? So the reason for this question is that it had been observed that Martin's maximum double plus and star tend to seem to imply have the same consequences for H omega 2. Okay. Now it was known that MM plus omega, so that is the form of Martin's maximum. Let's see. So Martin's maximum double plus says, suppose that you have, I didn't write down the definition, but I think most people know it. So suppose you have all of one many dense sets for, you have a forcing which pure stationary sets of omega 1. You have all of one many dense sets of it. And you have all of one many P names for that forcing for stationary sets of omega 1. Then filter G, which it intersects every dense set. And moreover, it interprets every name, each one of these names, as a true stationary set. Okay. Now you could define the same thing where you just don't have all of one many dense names, but just countably many. And so Paul Larson proved that MM plus omega. So this MM plus omega does not imply star. So that was known. Okay, so the result is this theorem together by myself and Ralph Schiller, which says that MM double plus implies star, right? So in particular, it's star is compatible with all large cardinals because you can force MM double plus from a supercompact with forcing of size a supercompact. So now I'm going to give a proof of the theorem and a full proof. As we will see, the main idea will be to use some L forcing.
Sorry, can you say
Yes.
again why? So why does this show that it's compatible with being with?
Well, I mean, take the supercompact kappa and then take any large kernel above kappa will be preserved, right? Because I'm forcing with a forcing of size kappa.
Oh, I see. Yes. Okay. Thank you.
Yeah. So as we will see, the main idea will be to use something called L forcing. The idea of L forcing goes back to Jensen. Okay, which I mean, I'll just say the idea just quickly in words, and then we'll see the application in this proof. So L forcing refers to the following situation. So you would like to add some object, and you don't, which lives, let's say, such that you have approximations to the object you would like to add, which live not in a set forcing, right, but in some outer model. Okay, and now we want to devise some forcing of finite sets of sentences that approximate, that give partial information about those intended objects. And that's what's known by as L forcing, right? I mean, and we have to say, well, this set of sentences is consistent in the sense that in some outer model there is some object which certifies these sentences, okay, which makes them, which shows that these sentences are consistent. So that's in a nutshell the idea about forcing, and the L is for language, because it's very linguistic, so forcing, and it's going to use side conditions, and the construction will be with a forcing which will be defined recursively. So, but it's not going to be an iteration. Okay, it's not an iteration, but it's some recursive definition of a forcing, and the forcing that will work in the end will be the last member of the construction. Okay. So a result of a similar flavor is the theorem of Tolorchevich that says the following. So suppose that every set of reals in L of R is recursively there, so you have large cardinals, And suppose there happens to be a Ramsey ultrafilter U. So then L of R of U is actually an LR generic extension of P omega mod phi, right? So every Ramsey ultrafilter is automatically generic over L of R for this nice forcing. Okay, so it's a similar, you know, it has it's a result of a similar flavor, right? We're saying, well, this natural nice inner model, actually very well studied inner model, is going to be you know, an actual generic extension of this same L of R, the same inner model. Okay, so here is the proof of the theorem. So right, so to start with, double plus implies AD and L of R, PFA suffices. So we only need to show that L of P omega 1 is a P max extension of L of R. Okay. So now I'm going to
what do you mean here by plus plus implies AD of L of R?
Right.
PFA suffices. PFA suffices for what?
To imply AD and L of R. PFA implies that AD holds.
Oh, I'm sorry. Yeah. Okay.
Okay. So here's a well-known fact that I'm going to use. I'm going to actually prove it. It has a nice proof. It was a well-known fact that if the non-saturated ideal is saturated and you have Martin's axiom, and you have some large kernel P omega 1 sharp exists, and then you have some A, which is a subset of omega 1 that computes omega 1 correctly, then the filter I've defined before, gamma A, is going to actually generate all of L of P omega 1. So this gamma A is a filter on P max, and it's equal to L P omega 1. L P omega 1 is L of R added to, you know, the extension of L of R with that filter, right? So gamma A is a set of P max conditions such that there's a correct iteration of Mi relative to the non-saturated ideal. So such that the final model is, every positive set in the final model is stationary, sending the distinguished set A to this big A. Okay. So we already know what the filter will be, but what we will have to prove is that this filter is generic over L of R. That's a non-trivial part. But let me give a sketch of the proof of this fact that I just showed you. All right, so let B be a subset of omega 1. Right now, I want to show that that it belongs to this. It's in the final model of some P max condition in that gamma A, right? So it suffices to prove that there is some MIA in P max such that there is some correct iteration. Actually, it's necessarily unique because these are models of Martin's axiom. A correct iteration of Mi relative to the non-saturated ideal, sending small a to big A, okay, and such that if J is a corresponding generic iteration map, then there's some B in M that is stretched up to become B, okay, this B that I want to capture. Okay, so how do you prove it? All right, so
where's the B from? I don't.
Oh, B is from the universe. B is from V, right? So
can you go back to the previous page again? I mean, is that where the B is mentioned first? No.
No. So I want to show that L of P omega 1 is L of R together with this filter, right?
Yes.
Hello.
Yes.
Yeah. So right. Yeah. So that's why. So it's enough to show that any subset B of omega 1 is in there. Okay. Is in gamma is in this extension. So it's enough to show that it comes from some MIA.
Well, that's where the B is from. Okay. B is some arbitrary subset of omega 1. That's given. And then you good. Okay, and also can I ask why? So why is this correct iteration necessarily unique?
Why is this what correct?
Why is it necessarily unique?
Oh, right.
page?
I mean, that comes from the general Pmax series. The fact that you have Martin's axiom, let's see, I mean, tells you that the generic filter depends on where you're sending A, because you have almost disjoint coding.
Okay.
It's an argument using the almost disjoint coding or some other. Yeah. Okay.
Yeah, thanks.
Right. So okay. So now to prove this, you take some theta large enough cardinal and some countable n that contains everything relevant. That would be A and B. And now let M be the image of N under its Mussorgsky collapsing map. All right. So this N. And now pi, this function pi from N to N is just its inverse. All right. So it's some elementary embedding. Now make M0, I0, A0 is just the image of everything under the collapse. All right. So I0 is the non-saturated ideal in this model. And that's going to be a Pmax condition by the fact that I have these large values, because P omega 1 sharp exists. You can show that that is actually iterable. I mean, that may not be true in general if you work in a minimal, without sharps. Okay, now we built an iteration. I'm going to build an iteration M alpha, I alpha, together with some filters and embeddings of this first guy, M0, I0, and some elementary embeddings into H theta, right? So this, so pi, this will be this pi alpha from M alpha into H theta, such that which commute, right? So so you have alpha less than beta, so then pi alpha, I mean, is the same thing as going to M beta and then taking pi beta, right? Now, for every alpha less than omega 1, let delta alpha be the height on M alpha, so it's an intersection with omega 1, and N alpha is its range. Okay, so yeah, so every M alpha is just a transitive collapse of N alpha, right?
Before you go to the next slide, so when you say here,
yeah,
by our hypotheses, what exactly, or can you sketch?
Right. I mean, you have to show. Yeah. I mean, the thing is, so the point is that you take any generic iteration long enough, of any length of this M0 I0, and the point is that that iteration will lift to a generic iteration of, adding all of L on top of M0 I0, right? Using the sharp, right? And with the same generic filters. And then there's the general fact that that model, because the length of the iteration is certainly shorter than the ordinals, will be necessarily well-founded, and therefore the original iteration was well-founded also.
Okay.
Okay. Now, so given alpha, I define G alpha as the set of all sets X in P omega 1 of the model M alpha, such that when I take the anti-collapse of X, well then delta alpha, the height of M alpha, is there. Okay? Now, by saturation of the non-saturated ideal, each G alpha is generic for P omega 1 mod, the non-saturated ideal of M alpha. So why is that? Well, that's true because every maximal anti-chain A of M alpha in this model, a size at most aleph 1 there. So it's okay. So right. So if you go to an alpha, which is isomorphic to it, via pi alpha, then you have some enumeration as psi less than omega 1 in N alpha, which enumerates pi alpha of A, together with the club C, such that for every delta in C, delta will be in S psi with some psi less than delta, right? So you have a club through the disjoint union. But then right. So but then okay. So that gives you the genericity of G alpha, right? But then each m alpha plus 1, which is will be the generic, if you define m alpha plus 1 to be the generic ultra power of m alpha by this g alpha, it's an exercise to see that it's actually the Mossopsy collapse of the Skolem hull of n alpha together with this delta alpha. Okay, that's just it's an easy verification. So you just get right. So you just m alpha plus 1 is just throwing in delta alpha to n alpha and collapsing. So in the end, of course, you get that B has been recovered by this. It's the image by this iteration in length omega 1, right? Okay, so that is proof. So okay, so since so I have that MM double plus implies the above hypothesis, right? It implies that the non-saturated deal is saturated, and of course implies that P omega 1 sharp exists and implies Martin-Jackson. So it suffices to assume MM double plus and prove that that nice filter gamma A is in fact generic over L of R. Okay. So for this, I take a dense subset D living in L of R, a dense subset of P max, and I'll prove that gamma A intersects D. Right. So that's what I need to prove. So so again, I know what my filter is. I just need to show that it meets every relevant dense set. Now, MM double plus implies, has this implies that every set of reals in L of R is universally bare, but moreover, the class of sets of reals in L of R is universally bare in a nice way. So that sort of you have a nice way to go from uniform way to going from a universally bare representation of the set to universally bare representation of the projection of that set, set in R to the n, and moreover, all generic extensions will agree on that. So okay, so that gives you that you can fix a 3T on omega cross 2 to the aleph 2 such that this 3T will project to a set of reals coding the members of my dense set D, right? And such that, and not only that, but also such that when you force with the collapse of omega 2 to omega, then that forces that T projects to, the projection of T codes the members of some dense subset of P max. Okay. So this, you can see that this is a statement that it's projected in two trees, it's projected in two sets of reals, right? One is D, and the other one is P max. Okay, so so this, I have this from MM double plus. So okay, so it will suffice to show that there's a forcing notion Q, which preserves tertiary sets of omega 1. So I want to apply MM double plus to it, and which forces that there is a branch X comma B through this tree T, okay, such that the projection of this branch of this X is a real that codes a member of gamma A. Okay. So if you look at this is saying, well, this is some sigma 1 statement in this about T, right? There's this infinite branch to this 3T, and you say that X will code some countable object, so that I have moreover I have this generic iteration of this guy, right? That sends its distinguished set to capital A, and moreover this iteration is such that every positive set in the final model is stationary. Okay, So that is something that you can apply MM double plus to, right? When you apply MM double plus to this statement I just described, you get exactly what you want to prove. Okay, is this clear?
Yeah, I think to me it is.
Okay, good. So, okay, good. So, all right. So that's our goal. So for this, we can do the following. So we let kappa be some large enough cardinal, so 2 to the, say, 2 to the power of 2 plus, so somewhere where this 3t lives. You know, you could actually, we could actually do, you know, you can just finding things a bit, you can do, we can do with kappa being all of 3, but it doesn't, I mean, it's conceptually just a bit more involved. So this is clearer. So, okay, so I take this kappa, and first of all, I do something. So I make sure that there is a diamond on H, on kappa, actually on H kappa. So what I do is I add a coin subset of kappa, right? Conditions of size and kappa. And so I'm not changing H kappa, but I'm adding this diamond sequence. So I have this club C of kappa, of ordinals, say about omega 2, and I have this sort of diamond sequence that will, you know, consist of models Q lambda and B lambda, lambda ranging in some club, such that the Q lambdas will form a strictly increasing and continuous sequence of transitive elementary submodels of H kappa of the extension, which is the same as V. Right, so we have this filtration of models, and then the B lambdas are subset of these models Q lambda, and this is a diamond sequence in the sense that if you give me any subset of H kappa, then there will be stationary many lambdas such that, you know, B lambda will be the intersection of the set with Q lambda. So it's enough to show that there is in this extension, there is a forcing P which preserves the sets of omega 1 and forces that there is a branch X comma B through that 3T such that the projection to the first coordinate codes a member of my nice filter gamma A. Okay. So from now on, I'll just write V for V of D. So assuming that I have this nice diamond. Okay, so the forcing P will be P kappa for a certain sequence, P lambda, lambda ranging over C together with you know, kappa will be this top element. And this will be a sequence of forcings defined. I can already, you know, tell you what the definition is. And so each P lambda will be the set ordered under reverse inclusion of those finite sets P of sentences in a suitable fixed language, okay, of size lambda, such that the collapse of lambda to omega forces that there is a lambda certificate for P. Okay, so this will be finite sets of sentences which are consistent in some strong sense.
What's a lambda certificate for P?
Yeah, that's what I'm going to define next. Yeah.
Okay.
So we will have that if every P lambda is a subset of Q lambda, right? And they will extend each other. So, you know, you have lambda 0, you know, less than lambda 1. The projection, the intersection of P lambda 1 to Q lambda 0 will be P lambda 0. And P kappa will be a subset of H kappa. Okay. All right. So let's see what the lambda certificate is. And for this, I first need to define the notion of lambda pre-certificate. Okay, so lambda certificate will be a lambda pre-certificate, which is particularly nice. Now, a lambda pre-certificate is always relative to some well, to H omega 2 with the non-saturated ideal on omega 1 and this distinguished set A that we fixed, right? And also relative to this 3T. Okay, so that will be a complete set of sentences capital gamma sigma in a suitable fixed language that I'm not going to define, but you can carefully design to do what I'm going to describe here. Anyway, so it's a set of sentences that describe finitary information about the following objects. So first of all, you have two Pmax conditions, so M0 and N0. These are basically reals. You will also have a real X, which is a sequence of k's, a real that will code N0 in some fixed way. And also you will have a branch, kappa n, alpha n less than omega, a branch through T. Okay, so you will define, this, and so you will have, constant symbols for these alpha n's and so on. Right, so you will have some generic iteration of M0 within N0. Okay, so this N0 is the universe of the strong of this script N0 condition. So you have a generic iteration of N0, right? That will witness that N0 is stronger than M0, right? As a Pmax condition. And then moreover, you will have a generic iteration of N0 of the strong condition in length omega 1. So that's the omega 1 of V, such that when you go to the final model and you look at the distinguished set there, this A star, that is precisely my distinguished set A. Okay, so far we have, yes, just what I said. Now you will have that, you can look at this sequence here of mi and pi ij.
So by complete, you just really mean maximal or what?
Yes.
What? Okay.
Yes, a maximally consistent, yes, set of sentences in some appropriate language. Yeah.
And the language will be countable though.
No, the language will be of size lambda.
Ah, okay. Oh, that's why it's called, yeah, okay.
Mm-hmm. Mm-hmm. Right. Okay, fine. So then I have so then I have the sequence mi together with pi's, which is the result of stretching the iteration that I started with of the weak condition, right, in length omega 1, right? So this sigma, remember, so let me just go back one slide. This sigma here was the sigma ij's were the embeddings corresponding to the strong condition. Okay, so this so look at this, look at the the image under this final map of the iteration of the weak condition. Look at the final model there. That's the actual H omega 2 of V with the non-saturated. Okay, so what this is saying so far is that yes, so you are absorbing all of H omega 2 into an iterate, generic iterate of some countable Pmax condition. Okay. Now you will have then a subset K of omega 1. So this will be the side conditions. And for every delta in K, you will have some lambda delta in this club C below lambda, right? We're defining P lambda, right? And so in such a way that if gamma is less than delta, which is an index for side condition, then lambda gamma is less than lambda delta, and X gamma union lambda gamma is contained in X delta. Okay, so this is saying I have this increasing this containment increasing sequence of models. Okay? Each X delta is an elementary submodel of Q lambda delta with B lambda delta with P lambda delta. So that's where the recursion comes in. Right? I mean, I have I've defined already P lambda delta, so I can talk about it in the definition of P lambda. Okay, so X delta is this countable elementary submodel, which is not in
V. P lambda delta is going to consist again of such complete sentences. The conditions are complete sets of sentences. Is that right?
Exactly.
Okay.
So P lambda delta is going to consistent in this. I mean, in this, this consistent, suitably consistent sets of sentences. Of course, for a slight, smaller language, right? I mean, of size lambda delta.
Yes.
Yeah.
So what are these lambdas? I forget. Where are they? Are they less than omega-2 or what are?
No. These lambda deltas are elements of this club C of kappa.
Ah, okay. Oh yes.
These are So all these Q lambdas are elementary submodels of H kappa. Okay. So they will. We will use the diamond sequence. This is come from this filtration that I took from H kappa into nice and elementary submodels.
Mm.
And then the trace of each x delta in section omega 1 is this delta, okay, this index of the side condition. So we have these side conditions, these models which are indexed by these countable ordinals, and you say, well, it's the model x delta has height exactly delta, and it's a model of lambda delta. It's a q lambda delta for this x lambda delta. Okay.
So wait, so the Q and the B come from the diamond, or what?
Yes, the B's are the members of the diamond sequence, and the Q's are these models on which B lambdas live. Yes.
And where do the X's come from?
The X's will be nowhere. I mean, these are some models that will exist.
They're constants of the language, or what are the X's?
I mean, you can have like constants that describe, and say, well, there's going to be some x delta, and I put this thing in x delta, and so the language will give some information about these x deltas. We'll approximate them. Yeah.
Okay. Mm-hmm.
And everything else, and everything I've mentioned so far.
So they're predicates in the language, or these x deltas?
Yes, you can take them as predicates. Yeah. Mm-hmm.
Okay.
Yeah, or like one predicate coding these things. I mean, there are various ways to do this. Okay, now, so now a lambda pre-certificate, sigma will be a certificate if in addition you have this condition triangle that says that for every delta in K, when you look at the side condition X delta, well, you have that the certificate is sort of like self-generic. The intersection of the certificate with X delta is it's generic for P lambda delta. So that means it intersects every dense subset E of P lambda delta, which is definable over the corresponding structures. So that's Q lambda delta with P lambda delta and B lambda delta from parameters in this countable model. Okay, so it really is like a side condition in the concept of proper forcing, right? Where you say, well, I require that this condition is generic for this model in some sense. Okay. And this will be crucial. I mean, that's the crucial element that makes everything work. So recall that a condition in P lambda is a finite set P of sentences that such that the collapse of lambda to omega forces that there is a lambda certificate sigma which extends P. Okay. Now this sequence is you can see that it's not difficult to see that it's increasing a continuous sequence of forcings, and they're all contained in P and H kappa, right? Once you design a language in a suitable way, right? Now, the first non-trivial thing we prove is that these forcings are non-empty. So why is that? All right, so let G be a generic filter for collapsing omega 2 to omega. And now take M0 to be H omega 2 from the V together with an unsaturated deal of V and my distinguished set A. Now in this extension, in this collapse, extension, that is a Pmax condition. Okay, that's again follows from my large cardinals that I have in V. So since the projection of T is a dense subset of Pmax in this model, in this model in V of G, there is a branch. There's a Pmax condition which is in V, right, which extends M0, right? So it means there is a branch Kn alpha n less than omega of T, such that the projection of the branch to the first component codes some Pmax condition M0, for which there is a correct, which is stronger than M0. So that means there's a correct iteration of M0, which was H omega 2 of V, witnessing that N0 is stronger than M0, right? Okay, so this I have. So now this iteration that lives in V of G, right, will naturally lift to a generic iteration of V, of all of V, using the same generics G alpha that I used in the original iteration, right? So that's a standard fact. I mean, so with the same generic filters, because P omega 1, is saturated, that's true. So you have this iteration Mi plus pi ij plus. Now go to the final model. So that's M omega 1 of N0 plus, okay? And let pi be the corresponding embedding. And that's, I'm going to focus on this model in a moment. Okay, now still living in V of G, I have that the theory of this iteration I've built, right? The bottom iteration, the Mi pi ij, and the Ni sigma ij iteration, and this branch through this tree, or rather pi of that branch, okay? And the empty condition for side conditions, because I have no side conditions yet. Well, that is a lambda certificate, or I should say a pi lambda certificate for the empty condition, okay? Relative not to the original parameters, but to pi of the original parameters, right? So pi of this H omega 2 and A and pi of T. Okay, so that's true in some outer model, namely V of G, right? So if you look at the way I've put together these objects, well, they satisfy all the definition of being a certificate, okay, relative to these parameters. Okay, but now there's a lambda certificate for the empty condition, now relative to pi of the parameters, and that's in the generic extension when I collapse pi of lambda to omega of over M. Okay, M was this model here. And that's simply because everything is coded by real, so that's by sigma 1 absoluteness. So that it was true in V of G, so it's true in this collapse extension of M. And now I can pull back using pi to something to say that in V, the collapse of lambda to omega forces relative to the intended parameters that that there is a lambda certificate for the empty set. Okay, so the forcings are all non-empty. All right. Now, so once you have a certificate, once you have a condition, so which is certified somewhere, right? Then, and if you ask any question about the intended objects, right? Then that question will have an answer there. So you can just add that answer to your conditions. Okay, and that will be a strong condition. So that shows that, so that's why I'm saying that standard density arguments show that if you have taken any lambda and you take G to be P lambda generic over V, and then you take these things to be the term model given by the generic filter, then that will be the sort of object that we want to have, okay, that we want to force. So this I will be generic iteration, actually which extends all of H omega 2 of V, right? As in fact, the M omega 1 will be like that. Then every stationary set in V is positive from the point of view of IN omega 1, second bullet point. The distinguished set of N omega 1 is the real A, and N0 is coded by a real projection of T. Okay, that's what you get just from, by this standard density arguments.
What did you mean by the term model?
Oh, well, right. So you have the generic filter, and then you simply look at all the information given by all the sentences in the generic filter. Okay, and then they will describe this model. That will be the model. Okay. So these are the options that you are reading off from the theory. Yeah.
Okay. Yeah. Okay. Mm-hmm. Sure.
I mean, you have to define the language carefully. You have to have constants for, for all countable orders, all kinds of things. Yes.
So, but when you say term model, I don't know, you mean like in the proof of the completeness theorem or something like that?
Yes.
Yeah. Okay. I see. Okay. Okay.
Okay. Right. So this is the situation that we are at. Okay. So we have these objects that we're adding. So, but now comes a crucial level. It says that now if you take any positive set in the final model that we obtained when we force with this forcing, okay, that will be stationary in V of G, and that will be enough to finish the proof, because that will immediately give you that of course that this iteration is correct in V of G, right? So just what the lemma says, right? And also that P preserves stationary sets of V, because every stationary set in V was positive in this final model, right? That was the second bullet point. All right, so it's enough to prove this, right? So an application of MN double plus to this P will yield the existence of this correct iteration of the P max condition coded by a real in the projection of T and hence in D. Okay, so here's how to prove the lemma. So let C dot be a P name for a club, omega 1, and this S dot is a P name for a set in this final model, and Q a condition in P. So I want to go to a strong condition, Q star that forces that there's some delta which is forced to be in S dot and which is in C dot. All right, so let lambda in C be such that Q lives in P lambda, okay, so, and B lambda codes this name intersection P lambda cross omega 1. So I'm looking at the name, at this name as a set of pairs, P comma mu, where P forces that mu is in the name. All right, so, that's where I use the fact that this is a diamond sequence. And this Q lambda together with the P lambda, right, and this intersection of C dot with P lambda is an elementary submodel of this structure. So, okay, so I can fix this lambda. Now I'm working in some collapse W of V. I could just find any P lambda generic filter G over V that contains this Q. And now let these be the objects that I get, given by this generic filter. Right? So these are the corresponding objects that I get that G gives me. So we call this what I just proved, right? That observed that the generic filter gives you the sort of objects that we want. Now, okay, now we may extend this iteration of length omega 1 of V, right, to an iteration of length omega 1 of W of this outer model, this collapse extension. Such that delta being the omega 1 of V is in the image of S dot. And that's simply because S dot is positive in that final model, so I can just simply take G delta to contain S dot, and that will force this. Okay. So that's how I continue my iteration. And now let I be the stretch out of the I0 iteration to length to an iteration of length omega 1 of W. Okay, so that's the type that should be so the length of this iteration should be omega 1 of in W. Okay, now right. So now look at this iteration. The restriction of the iteration between delta and W and omega 1 of W, right? And write it like this. So that's some iteration of of h omega 2 of v, right, in length sum w, right, and that lives to a generic iteration by the usual argument of v, using the same generic filters as in I. Okay, so now go again. So go back to go to the final model, and that's m omega 1 plus. That should be omega 1 w plus, and pi is the pi delta omega 1 plus, right? Now by an elementarity argument, as in the proof when we prove that the p lambdas are non-empty, there'll be in V some condition Q. I'll give the argument in a moment. This Q star stronger than Q, for which there is some delta. There's a side condition. There's some index in the side condition part of it. Okay, such that Q star will enforce that delta is in S dot, and this lambda delta will be this lambda, where everything relevant is living. And in particular, the existence of the model X delta will be witnessed by the pointwise image under this pi of Q lambda. So remember that G was generic and was obviously meeting every dense set that is in Q lambda. Okay. So let's see, just sketching of this argument. Well, let X G mu for mu in A be all the generic side conditions that are mentioned in Q, in the condition Q, right? And now look at these, the image of everything relevant on the pi. So if you look at these objects, so this branch through pi of t, and this iteration here, right? And this iteration I together with the pointwise image on the pi of every x mu, and together with this new side condition x lambda being the pointwise image on the pi of q lambda. So all these objects will form in this W a kappa certificate of or pi kappa certificate for pi of q together with these new sentences that say, well, let's say the following: say that delta is forced to be in pi of s dot, and then and then x pi lambda exists. So I have a side condition there. Should say that yeah. So this and pi lambda is I guess the lambda of delta, right? The index responding to delta, right? And pi and x pi lambda intersection omega 1 is delta. Okay. Right. So these objects certify this condition. So by sigma 1 absoluteness in the collapse extension of M by by collapse pi of kappa to omega, there's some delta together with some pi kappa certificate for this very this for this condition. Okay. Right. Okay. So right. So therefore, by I could pull everything back to V, and I have that in V in the collapse of kappa to omega in V. There's some delta in less than omega 1 together with some kappa certificate for precisely this condition. Okay. So that is my Q star. Right. But now I finally, since Q lambda, P lambda together with C dot intersection P lambda was elementary in this structure, a density argument, by a density argument, this Q star will force that delta is a limit point of C dot, and therefore in C dot, because C dot was forced to be closed. And that's where I use the crucial clause in this triangle, the self-genericity condition clause. Okay, so let's see that. So let's take some Q prime, which is smaller than Q star, and some condition and some silence in delta.
What can you show us delta again, maybe?
Delta again. This delta was this condition. Yeah, this one here, right? Which says that the intersection of the certificate, right, with X delta meets every dense set that happens, which is definable.
It's like this local genericity for.
Yeah. This local
genericity. Okay. Mm-hmm.
Okay. So we were right, yeah, here, right? So so you give me some q prime stronger than q star and some psi less than delta, and I need to find you some condition q double prime which will extend q prime and some x prime between psi and delta, that so q double prime forms that psi prime is in c dot, right? Now take any kappa certificate, capital sigma for this q prime, right? Will contain, so look at any kappa certificate and look at the corresponding x delta. Now by this local self-genericity, this x delta will contain some r, right? So this certificate will contain some r in x delta, which forces some ordinal psi prime above psi to be in c dot. And that's thanks to the fact that this set here, E, set of conditions are in P lambda, so that there is some psi prime above psi, so that R forces that psi prime to be in C dot, is a then set definable over this structure from psi, which is in X delta. So, but of course, X prime is less than delta because R is in X delta, and the height of X delta is just delta, is precisely delta. But then R union Q prime will be a common extension of R and Q prime in P and will force what I wanted, right? Because a common extension is certified by the same certificate, sigma. Okay? Forcing this. So, okay, so that finishes the proof. So I still have some time. Right, so, okay, so here's two corollaries. So MM double plus implies, implies these things that we were not known how to force, that were known to follow from star, but it was not know how to force them over, set C model. Okay, so I have a lot of stuff here that I'm not going to go through, but I wanted to mention some things. Okay, so first of all, I want to observe that, so this forcing P is a version of number forcing in some sense. And that is why our forcing P, so note that our forcing P absorbs H omega 2 of V in a generic iterate countable model, right? So now, so if you take a sequence alpha n converging to omega 1 of n, so it's countable, there's such a thing, because you are, always taking it, taking ultra powers by, generic ultra powers by p omega 1 mod something. So this sequence here of the j alpha n's will be cofinal in the final omega 2 of V. Okay. So
well, I don't understand even the first sentence. Our forcing absorbs H omega 2 V. What does that mean?
Well, I mean that you have this generic, this Pmax condition M0, and you added this generic iteration of it that absorbs all of H omega 2. H omega 2 is actually the final condition of M, what we call M omega 1, right?
Oh, I see. That's what you, okay.
Yeah. So okay, so this so this behaves a bit like number forcing. So the question is, does P add a V generic number forcing? Also, the question is, can arbitrary instances of P for various dense sets D be iterated? For example, using the revised countable support, right? Because number forcing can be iterated using revised countable support by Scheller. If you could do that, then you should be able to force star starting from an inaccessible limit of Wooden particles. But that's not, no. So you would be forcing instances of, combining this forcing P with forcing the non-saturated ideal on omega 1 to be saturated by just killing the next Wooden particle.
So now, if you want to start for star, you have to start with what? With a Wooden limit of Woodens, or with a measurable limit?
I mean, the best that's known is by so result of Leeds and Schindler. They get I think so that's if you have an accessible of cardinals kappa, so the kappa is kappa a kappa double plus superconduct, so it's quite strong. And then you have some Wooden cardinals above the inaccessible. Then you can force star. But I think that's the best that you can do in general.
Oh, wow, okay, that's far stronger.
Sure. Yeah.
And what is known about the lower a lower bound?
Well, I mean, you know, it's well infinite many woods. I mean, you know, that's what
Okay.
you can do.
Yeah.
Right. I mean,
so
actually,
this would be pretty much optimal, I guess, if you inaccessible limit of wooden cardinals. I mean,
the question is, well, I mean, we know what the consistency strength of star is just you know, it's that of AD. I mean, it's infinitely many wooden cardinals because you can force it over the bar. But the you know, what's really interesting would be how, you know, what do you need in order to force it over model ZFC, right?
Oh, I see. Okay, right. Yeah.
That's a real question.
But that's actually not too far from, I mean, it's not very far from infinitely many woodens. Not horribly, not like super compact or something like that.
Well, right. Okay. Now, okay. What else can I do? Maybe I should. I mean, I have lots of other, many more slides, but I think I should probably stop, right? Or what do you? Because you said, I mean, there should be time for questions, or should I talk a bit for? Well, up to you. I mean, should I talk for another 5 minutes or 10 minutes?
I think you can talk for another 5 minutes. Yeah.
5 minutes. Okay.
Go ahead.
All right. So I'm going to mention this. All right. So since we're talking about number forcing, I will mention number forcing like honest absoluteness. Okay. So that refers also actually to the notion of honest consistency. Oh, actually, this should be honest consistency, not absoluteness. So when Ralph talked about this a year ago, he focused a lot on the concept of honest consistency, and that's the idea is that you know, I mean, you have something which is in some outer model which is not necessarily a forcing extension, and you want that to somehow reflect that down to V. So okay, so it turns out we can elaborate on this proof and prove something along these lines, but it's still very partial. So anyway, so let's BMN double plus COF omega sub kappa be this natural bounded form of an N double. So I would say, well, take some X in H kappa plus. Okay, so I'm going to say something about things of size kappa, and phi is sigma 1 formula in the language for this structure. And suppose it's stationary preserving forcing, which forces this statement to hold in H kappa plus, but also it forces that the cofinality of every regular cardinal between aleph 1 and kappa, so above aleph 1 and up to kappa, is countable. Okay. So then there are in V essentially many sets N of size aleph 1 that reflect this statement. Okay. So BMM plus plus, when this subunit is aleph 1, is just BMM double plus. That's not saying anything. Okay, so you know, there's a form of this, you know, for forcings which are like number forcings. So a variation of the proof I presented gives the following. All right, so suppose there's a proper class of wooden cardinals, and let kappa be a cardinal between aleph 1 and less than aleph omega 1. And that's a funny restriction that we have to impose. And suppose you have this this forcing axiom. Then you have this statement that you have take any X in H kappa plus and take a sigma 1 formula phi in this language, and suppose that for every universally bare set A, there's some collapse extension. So in some outer model, there's some, you know, there's some transitive model W, which is A closed. Okay, so it's sufficiently rich. It contains H theta. It's H theta. So no, this should be H kappa plus, right? Sorry, V. No, that's fine. No, that's fine. What it says here. Yeah. So it contains quite a chunk of V, and then also it's correct about stationary sets of omega 1 in V. It doesn't destroy any stationary set of omega 1 in V. Also makes it's such that every regular cardinal between aleph 1 and kappa of V has been made cofinality omega, and it satisfies this phi. Okay, we're just talking about some outer model. Now there are in V such, again, you have this, you have that you can reflect this down to V. Okay, so this is like an approximation of this, well, of what I'm just going to mention here. Well, you could define, say that a sigma 1 statement is omega consistent in case for every universally paired set A, there's some closed transitive model, you know, so this a closed transitive model W of set of C star in some outer model that is correct about a sensual sense of omega 1 and satisfies that statement. And then you can define this axiom, and then star double plus, that says that every sigma 1 statement which is honestly consistent in this sense is reflects in down to V, like this. So yeah, so the theorem I just mentioned shows that a natural fragment of this thing follows from and then double plus, but it's an interesting open problem whether this is consistent, and it could actually be equivalent to an double plus. And yeah, okay, I think I'll just stop here. Okay, thanks.
Okay, thank you, David. Are there any questions from the audience?
Show the next slide that you had on for a few seconds.
Oh, okay. So now I was going to talk about okay, the non-uniqueness of forcing complete theories for H omega 2, right? So I mean, this nice feature of star is that it decides, you know, completely decides the theory of H omega 2, right? So, but that's not the only forcible axiom that provides this complete picture, or say sigma 2 axiom, because you could, but this, okay, that's an easy argument. So you could consider, for example, the axiom that says, well, I'm an extension of a model of star by co-enforcing. Okay, so right. So of course this is consistent if because by the main theorem we know that we can force star, and then you can force with co-enforcing on top of it. And then another point is that co-enforcing is a forcing H omega 2, which is definable, homogeneous. It has the Aleph-2 chain condition, so the H omega 2, you know, the extension is the extension of the H omega 2. And well, so for these reasons, it will also completely decide the theory of H omega 2 and will imply that there are Susan trees. So I mean, okay, so that was the first observation, that you know, completeness is not, you know, star is not the only axiom that gives you this sort of completeness. That was the first slide, but there are more things.
Well, okay. So I don't know what. So you're saying the theory is different after you do co-enforcing? Yes,
I mean it's, yeah. I mean, I'm not saying anything deep. I mean, saying you know, I mean,
but
you can say.
Is this just true for co-enforcing, or can you do? Okay,
no, you can do with other forces.
You can do other things as well.
You can do other things, yes.
Cool.
There's some nice questions here. I mean, some things that these I don't know how to do. I mean, you know, that you could, you know, I mean, you could ask, is there a nice, you know, homogeneous forcing that does this sort of, that forces this sort of statement? Yeah. But maybe, okay. Maybe I can finish with the question.
Yeah, yes, do that. I think there are no questions from the audience.
No, right. No, I was gonna
just
mention.
Go ahead.
Okay. Okay, I wanted to mention this. Okay, that's the last slide. Okay, so you could ask for it's a obviously a difficult question. So is there a force, if you have large kernels, is there a forcible sigma 2 axiom A that decides the theory of H on X3 modulo force? Okay. So MM double plus will not decide the theory of H on X3.
Modulo forcing, you mean that forcing doesn't change the theory?
So that in the sense that star is complete. So any forcing extension of A will all agree on the theory of H on X3.
Mm-hmm. Oh, I see.
So yeah, I mean, I should point out that so MM double plus is not complete for H on X3, but it's not completely obvious.
What is why is it not complete for H omega 3?
Sorry?
What is the counterexample to this completeness?
Well, you can something in terms of the strong club guessing, holding or failing. You can make it at omega 2. You can play with that.
Huh. I see.
But it's not completely obvious. I mean, I couldn't find any easy principles that are easy to about H omega 3, which are not decided by MM double plus. Okay, I mean, there are such things, but it's not. It would be nice to find nice natural examples.
Okay, I don't have any further questions. Does anyone else have a question? Last chance.
Just a comment for David. I think that this results that you mentioned and the ideas on Namba forcing like honest absoluteness, that they're well, I guess they're very much connected to the things that Boban has been thinking about and that I've been working on with him. So I think it would be very nice to sit together at some point and compare what.
Yeah, sure. Yeah.
What are the ideas? Yeah.
Okay, so thank you again, David, for this talk. And I guess that ends our session.